Effectively grounding an electrical system with two separate services in one building requires careful attention to detail and adherence to electrical codes. Here is a breakdown of the steps involved. Firstly, verify existing ground connections. This involves confirming that the ground wire or wires attached to the wireway for the second service are indeed connected to the transformer ground. A ground resistance tester can be used. Other conductors can be traced back to the transformer to confirm the connection. Secondly, ground the 400 amp fuse disconnect. Install a 1/0 American wire gauge or larger bare copper ground rod near the 400 amp fuse disconnect. Then connect the ground rod to the disconnect enclosure using a ground clamp or exothermic weld. It is important to ensure all connections are tightened to create a solid electrical path. Thirdly, bond the two services together. Connect the ground rods for the two services using a number 6 American wire gauge or larger insulated copper bond wire. Install the bond wire between the ground rods or between the disconnect enclosures. This creates a common ground reference for both services. Fourthly, ensure that all raceways containing electrical conductors have a continuous ground path. Connect the raceways to the main ground busbar in the electrical distribution panel or switchboard. If any raceways do not have a ground wire, install one immediately. Fifthly, verify ground resistance. Use a ground resistance tester to measure the resistance between the ground rods and the electrical system. The resistance should be below 25 ohms for a 400 amp system and below 10 ohms for a 350 MCM system. If the resistance is too high, additional grounding measures may be needed. Sixthly, consider installing a surge protection device, SPD, to protect the electrical system from voltage spikes and transients. The SPD should be connected to the main ground busbar and should be rated for the appropriate voltage and current levels. Lastly, inspect and maintain the grounding system regularly for corrosion, loose connections, or damage. Test the ground resistance periodically to ensure it remains within acceptable limits. Make any necessary repairs or upgrades promptly to maintain a safe and reliable ground. Grounding ensures a safe path for fault current, protecting equipment and personnel from electrical shock and damage. A properly grounded electrical system is vital for safety and reliability. The process starts with verifying existing connections and moves to grounding the disconnect. Bonding the services creates a common reference, while grounding raceways ensures a continuous path. Verifying the ground resistance ensures effective grounding. Surge protection adds an extra layer of defense, and regular maintenance keeps the system reliable. Grounding the 400 amp fuse disconnect involves choosing the right size ground rod. A 1/0 American wire gauge or larger bare copper ground rod is recommended. The location of the ground rod is important. It should be installed as close as possible to the 400 amp fuse disconnect. Connecting the ground rod to the disconnect enclosure requires a secure method. A ground clamp or exothermic weld can be used. The choice depends on local codes and specific installation requirements. Tightening all connections is essential. Loose connections can increase resistance, reducing the effectiveness of the grounding system. Bonding the two services involves using a number 6 American wire gauge or larger insulated copper bond wire. The wire should be long enough to connect the ground rods of both services. The bond wire can be installed between the ground rods themselves or between the disconnect enclosures. A common ground reference is created when the two services are bonded. This ensures that both services are at the same potential, reducing the risk of voltage differences and electrical hazards. Grounding the raceways is another important step. All raceways containing electrical conductors should have a continuous ground path. This means that the raceways must be connected to the main ground busbar in the electrical distribution panel or switchboard. If any raceways do not have a ground wire, one must be installed immediately. This is typically done by pulling a ground wire through the raceway and connecting it to the ground busbar. Verifying ground resistance involves using a ground resistance tester. This device measures the resistance between the ground rods and the electrical system. The resistance should be below 25 ohms for a 400 amp system. For a 350 MCM system, the resistance should be below 10 ohms. If the resistance is too high, additional grounding measures may be necessary. This could include installing additional ground rods or improving the connections to the existing ground rods. Installing a surge protection device, SPD, is a proactive measure. An SPD protects the electrical system from voltage spikes and transients. These surges can be caused by lightning strikes, utility switching, or internal equipment malfunctions. The SPD should be connected to the main ground bus bar. It should also be rated for the appropriate voltage and current levels. Regular inspection and maintenance are crucial. The grounding system should be inspected regularly for corrosion, loose connections, or damage. The ground resistance should be tested periodically to ensure it remains within acceptable limits. Any necessary repairs or upgrades should be made promptly to maintain a safe and reliable ground. The NEC, National Electrical Code, provides guidelines for grounding electrical systems. Adhering to these guidelines ensures that the grounding system is installed safely and effectively. Grounding is not a one-time task. It requires ongoing attention and maintenance to ensure that the electrical system remains safe and reliable. Ignoring grounding can have serious consequences, including electrical shock, equipment damage, and fire hazards. Effective grounding is a critical component of electrical safety. It protects people and property from the dangers of electrical faults and surges. It's important to understand the principles of grounding and to follow best practices when installing and maintaining grounding systems. In addition to the steps outlined above, there are other considerations that may be relevant to specific installations. For example, in some cases, it may be necessary to use a ground grid to provide a more effective ground. A ground grid is a network of interconnected ground rods that is buried beneath the surface of the earth. It provides a larger surface area for grounding, which can be helpful in areas with poor soil conductivity. Another consideration is the type of grounding electrode that is used. Ground rods are the most common type of grounding electrode, but other types are available, such as ground plates and concrete-encased electrodes. The best type of grounding electrode to use will depend on the specific soil conditions and the requirements of the electrical system. It's also important to consider the size of the grounding conductors. The grounding conductors must be large enough to carry the fault current that may occur. The size of the grounding conductors is determined by the size of the electrical system and the type of equipment that is being grounded. Finally, it's important to document the grounding system. This includes keeping records of the location of the ground rods, the size of the grounding conductors, and the results of ground resistance tests. This documentation will be helpful for future maintenance and troubleshooting. Effective grounding is a complex topic, but it is essential for electrical safety. By following the steps outlined above and consulting with a qualified electrician, you can ensure that your electrical system is properly grounded and protected. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you are not comfortable performing the work yourself. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. When dealing with electrical systems, always prioritize safety and follow all applicable codes and regulations. Grounding is a fundamental aspect of electrical engineering. It's designed to provide a safe path for electrical current in the event of a fault, protecting people and equipment. Understanding the principles behind grounding is crucial for anyone working with electrical systems. The goal of grounding is to create a lower impedance path for fault current to return to the source. This allows the overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and de-energize the circuit, preventing electrical shock and minimizing damage. A properly grounded system also helps to reduce electromagnetic interference and improve the overall performance of electrical equipment. There are several types of grounding systems, each with its own advantages and disadvantages. The most common type is the equipment grounding system, which connects the non-current carrying metal parts of electrical equipment to ground. This includes the metal enclosures of appliances, motors, and other electrical devices. Another type of grounding system is the system grounding system, which connects the neutral point of the electrical system to ground. This helps to stabilize the voltage and prevent overvoltages. Grounding electrodes are used to connect the grounding system to the earth. Ground rods are the most common type of grounding electrode, but other types are available, such as ground plates and concrete-encased electrodes. The choice of grounding electrode depends on the soil conditions and the requirements of the electrical system. The National Electrical Code, NEC, provides detailed requirements for grounding electrical systems. These requirements are based on years of experience and research, and they are designed to ensure the safety of electrical installations. It's important to follow the NEC requirements when installing and maintaining grounding systems. Grounding is not a static process. It requires ongoing monitoring and maintenance to ensure that the grounding system remains effective. Regular inspections should be conducted to check for corrosion, loose connections, and other problems. Ground resistance tests should be performed periodically to verify that the grounding system is still providing a low impedance path to ground. Effective grounding is a critical component of electrical safety. It protects people and property from the dangers of electrical faults and surges. By understanding the principles of grounding and following best practices, you can help to ensure the safety and reliability of electrical systems. Remember that electrical work can be dangerous, and it's always best to consult with a qualified electrician if you are not comfortable performing the work yourself. This information is for general guidance only and should not be considered a substitute for professional electrical advice. Always prioritize safety and follow all applicable codes and regulations. Grounding is a critical safety measure in electrical systems. It protects against electrical shock, equipment damage, and fire hazards. This process involves creating a low resistance path for electrical current to flow back to the source in the event of a fault. This path allows protective devices, like circuit breakers, to quickly interrupt the circuit, preventing dangerous voltage levels from persisting. In a building with two separate electrical services, effectively grounding the system requires careful attention to both services and ensuring they are properly bonded together. The primary goal is to establish a common ground reference point for both services, minimizing the potential for voltage differences between them. This common ground reference is typically achieved through a grounding electrode system, which includes ground rods, ground plates, or other approved grounding electrodes. The NEC, or National Electrical Code, provides specific guidelines for grounding electrical systems. These guidelines outline the requirements for grounding electrode systems, grounding conductors, and bonding connections. Adhering to the NEC is essential for ensuring a safe and compliant installation. When dealing with multiple services in a single building, it's crucial to bond the grounding systems of each service together. This bonding creates a common ground plane, which helps to equalize voltage potentials and reduce the risk of electrical shock. The bonding connection should be made with a conductor that is sized appropriately for the largest service in the building. In addition to bonding the grounding systems, it's also important to ensure that all metallic enclosures and raceways are properly grounded. This includes electrical panels, junction boxes, and conduit runs. Grounding these metallic components helps to provide a safe path for fault current to flow back to the source. The grounding conductors used to ground these metallic components should be sized according to the NEC guidelines. Regular inspection and maintenance of the grounding system are essential for ensuring its continued effectiveness. Grounding connections should be checked for tightness and corrosion. Ground resistance tests should be performed periodically to verify that the grounding system is still providing a low resistance path to ground. Any damaged or deteriorated component should be replaced promptly. The installation of surge protection devices, SPDs, is also recommended. SPD help to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. These devices divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD should be installed at the service entrance and at any other locations where sensitive equipment is located. Effective grounding is not just a matter of following code requirements. It also requires a thorough understanding of electrical principles and best practices. Working with a qualified electrician is essential for ensuring that the grounding system is installed correctly and safely. Electrical work can be dangerous, and it's always best to leave it to the professionals. Improper grounding can have serious consequences, including electrical shock, equipment damage, and fire hazards. By taking the time to properly ground the electrical system, you can protect yourself, your family, and your property from these risks. Remember that grounding is an ongoing process. It requires regular inspection and maintenance to ensure that the grounding system remains effective. By staying vigilant and addressing any issues promptly, you can help to maintain a safe and reliable electrical system. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before performing any electrical work.